Hello and welcome to the second video of the 12th exercise session of Mathematics 1. So now we're going to have a look at optimization. So if you scroll all the way back up, you can see some kind of theory overview again. And 1.1 is finding an extremum in multivariate functions. And basically it follows much the same steps as it would do for one variable functions, just with a couple of little things you need to be wary of. So let's go through it again. First, we need to check, are there constraints to our functions? Are there asymptote roots, limit, that, and stuff that we need to be wary of? Then 2, we need to calculate our partial derivatives, which we learned how to do in the first video. Then we need to find critical points. So this is the part where we're going to have to be a little bit, do a little bit different than what we did with one variable functions. And then we get to point 4, and there you see that we see our second order derivatives and I gave them some kind of name. So A, B, C, and D. Well, where this comes from, it comes from the Jacobian, which is some kind of matrix. Well, for those who remember matrices from high school, well, basically you can take determinants of that and you end up with this. I'm not going to go much further into that. This is really something you will see in Mathematics 2 and you will go in much more depth. But basically what it means is that A, B, and C, which are our second order derivatives, well, they will tell us much about how our function is behaving and whether we're dealing with a local maximum, a local minimum, or we're dealing with a saddle point, which is kind of like a multidimensional inflection point. So those are the things you really need to consider. Okay, and then at the end, you see some kind of rules of thumb where we say if D is greater than 0 and A is greater than 0, it means you're dealing with a local minimum, and you can continue reading the list on by yourself. Okay, so I guess really the proof is in the pudding, so let's try that one. We're going to start with exercise A, and here I have to make sure that I do not copy it wrongly. So we have fxy is equal to 6 minus x squared minus yx minus y squared. Okay, so first things first, are there any constraints? No, there's nothing we really need to be worried about. It looks kind of like a polynomial, but a multidimensional polynomial. So in this case, let's start with finding our derivative with respect to x. So remember, y is a constant, so that means we end up with minus 2x. Well, this is just 0. Then here it is minus y, and this is just 0 again. Okay, let's do it now with respect to y. Okay, what do we get over here? We end up with minus x, and then here minus 2y. Okay, so now that we know this, well, what can we do? What can we do with that further? Well, now we need to evaluate this. We need to find a critical point. And how do we find a critical point? Well, the critical point is by recognizing that they both need to be equal to 0 at the same time. So imagine that we go all the way to my very first slide that we discussed is, well, we're gonna reach only some kind of real optimum of our function if they're both 0 at the same time. So we end up with some kind of like peak as we do over here. Of course, there are other ones over here where they kind of do the same thing. I think here you can see that there are smaller ones as well. So you see that there may be many possible candidates to have a maximum. But these functions are a little bit more simple. So let's have a look at this over here. So here we say, well, these two, when are they equal to 0? Well, they both need to be equal to 0 at the same time. So let's now solve this set of equations. Meaning that if we look at this, it means that y is equal to negative 2x, right? Okay, and if we know that y is equal to negative 2x, it means that minus x minus 2 times negative 2x is equal to 0. Okay, if we solve that a little bit further, what do we get? Well, here we get 4x, so we end up, so this becomes 4x, so we end up with 3x needs to be equal to 0. Well, that only happens when x is 0, and if x is 0, it means that y is 0. So we have one critical point that we need to evaluate, which is the point 0, 0. And well, if we fill it in here completely in the function, we end up at 6 for our function. Okay, let's evaluate what this means and how we can have a look at this further. Okay, over here, we need to take a second order derivative now with respect to x. And that one was called a. So let's do that. With respect to x, it's negative 2, which is smaller than 0. Then let's calculate c, which is our second order derivative with respect to y, which in this case, it would give us negative 2 as well. Then let's calculate b, which is our mixed term, second order derivative with respect to x and with respect to y, which in this case is going to give us, let's do it of this one, is going to give us negative 1. Okay, let's calculate d. d is, and here I'm just going to say, well, this is the formula, remember it like this. It comes from somewhere. I don't like doing this, but well, if I go into this, there's many other things you need to see before. So it's ac minus b squared, which is, in this case, negative 2 times negative 2 minus 1 squared, which would give us 3. So in this case, a smaller than 0 and d is greater than 0, meaning that we have a local maximum at 0.0.6. Well, if you plot these functions, you will see that the exercise we see here right now, this is going to be a true maximum. But to be completely sure of that, there are many other tests you need to do and there are many other things you need to consider. So for now, we assume that you don't know because you don't know how to test for these things. So just say, well, the best guess I can make is that it's a local maximum. Okay, let's do one more together. Let's do exercise E together. Let's write down what we have over here. We have fxy, which is equal to x plus 1 over 3 y to the power of 3 minus 1 over 2 xy squared. Okay, are there any asymptotes that we need to be wary of? Anything, discontinuities? No, not really. So we can just take our first order derivative with respect to x, which would give us 1 plus this 0, and this one here, it becomes minus 1 over 2 y squared. Let's now do it with respect to y. With respect to y, which would give us 0. 1 over 3 times 3 is just 1, so it would just give us y squared minus 1 over 2 times x times 2y. So great, this and this is also going to disappear, so you just end up with y squared minus xy. Okay, again, what do we need to do? Well, we need to find its critical point, so that means where they're both equal to 0 at the same time. Okay, let's have a look at this. So what does this mean? Well, we can rewrite our first equation, and what do we get? Well, we get that bringing 1 to the other side, we get that 1 over 2 y squared is equal to 1, or in other words, y squared is equal to 2, is equal to 2, or even in other words, we can say that y is equal to plus minus the square root of 2. Okay, great. What do we end up with over here? Well, we can fill that in. We can say, okay, this is 2 minus, because this is the square root, the power of, so we already knew over here that y squared was equal to 2, so this is 2, minus x times, here in this case, what do we end up with? Well, here we have to be careful. It's going to be plus minus, so x is going to times plus minus the square root of 2 is equal to 0. Okay, let's rewrite that once more. So of course you can split it up in two equations, right? So what do we end up with? Y is equal to plus minus the square root of 2, which in this case would give us that x, bringing 2 to the other side, x, so let's let's write it, plus minus the square root of 2 times x is equal to 2, which will tell us that y is equal to plus minus the square root of 2. And here, well, it becomes x over plus minus the square root of 2, which tells us that, well, because 2 is only written square root of 2 times square root of 2, which means that what we get over here is x is equal to plus minus the square root of 2 as well. Okay, great. So now that we have this over here, we can continue, because now that means that we have a critical point over here at where x is plus minus square root of 2, so we have two critical points. We have where y is plus minus square root of 2, and then we have where fx is equal to plus minus square root of 2 plus minus square root of 2. So that's going to be our critical point. So let's derivate it once more. And we can say, well, this is a, so our second order derivative with respect to x, which in this case is just going to be 0. Okay, let's do c with second order derivative with respect to y, which will give us 2y minus x. Okay, so again, still a function. Then here we get b, which is going to be, in this case, the second order derivative of x then to y, or in other words, let's do this one over here, it is equal to negative y. Okay, let's evaluate this now once for d. So what could you do here if you really want to know, well, whether it's greater or less than 0? Well, sometimes you need to fill in these points. Here, of course, h is equal to 0, so we only have to say that much about it. But, well, we need to, if you want to know, well, what the sign is of b and c, you need to fill in these things. So let's evaluate d. So d is a times c, so 0 times 2y minus x minus, okay, so over here, minus, well, b squared, so that's negative y squared, which would give us negative y. So here, let me move that squared up, negative y squared. Well, we know what y squared was. Well, we knew it was equal to 2, so this is going to be negative 2. Of course, you could have just filled it in from here as well. So this tells us that d is smaller than 0 for both of our points, right? If you fill them in, you will see that it's for both of our points, meaning that we have a saddle point at both points. We have a saddle point at, let me write it like this, saddle point at square root of 2, square root of 2, function value, square root of 2, square root of 2. And we have one at, let me rewrite it, at negative square root of 2, negative square root of 2, and the function of negative square root of 2, negative square root of 2. So here we have again a saddle point. Okay, so this is it for non-constraint optimization. I will recommend you that you make the following two exercises at home. You can make exercise D and F. Okay, good luck. See you in the third video.